The process of XRF has got 5 steps as we've described it here. This is showing the window that I described on the front of the system that's about the size of a dime. You would want that window to be on or near the sample. It doesn't have to be exactly on it, but the sample has to be in front of the window. It's best to put it on it. You pull the trigger to activate the X-ray tube, and then steps 2, 3, and 4 are really things that the user doesn't see. The X-rays excite the sample, knock an electron off, and as part of that instability, the system shifts its electrons around, emits a photon of energy that is characteristic to the element. We capture it as part of a spectrum of energy, and the part again that is visible to the user is that we come up with a grade match and a measured chemistry on the display. So pull the trigger, see the result. These steps are the things that go on in between. Here's another view of the same information. We've got the Bohr model of the atom, nucleus, electrons, orbital that the electrons are in. We shoot in our X-ray. An electron is knocked out of its orbital, knocked out of its shell. The result is that the electrons shift to go back to electrically neutral, and there's a fluorescent photon that comes out, and that energy will be specific to the atom that we've excited. So every element has a different signature energy that it emits. And this is just an animation of that process. Now, of course, we show ourselves ionizing 4 atoms and getting 4 different photons back, but in reality, XRF is a statistical method, and we can be exciting up to 100,000 photons in a second, not 4 in 4 seconds, and we process that information to determine the concentration in the sample. Here you're looking at the spectrum, and chrome has a lower energy than iron, than nickel, than moly, and the height of the peaks is directly related to the concentration of the elements. So if there were twice as much chromium, we would have twice as high a chromium peak, and so forth. And then the part that is visible to the user is the display, where the chrome comes up not as a peak on an energy spectrum, but as the amount of chrome in the sample. So the way that it works is that we capture the spectra, we subtract out interferences, we make corrections for background and interfering elements. We apply our calibration factors to the net signal, and then what comes out of the other end is the elemental concentrations. The elements that we can test are circled here by the red boundary. Basically from magnesium to plutonium is what we can do. Magnesium is the lightest element that we can test. The things that we can't do that are common to real-world applications into alloy testing would be things like carbon, oxygen, nitrogen, sometimes beryllium or boron. Anything lighter than magnesium, lower Z number in this chart would not be measurable. We measure these elements, we normalize to 100%. That allows us to correct for size and shape, and that's the method that's used.
Today we got in a couple of pieces of angle. When you look at the angle, it looks so similar that we're not always sure what it is. So when we use our analyzer, we make sure to go up to it, have a nice clean surface, pull the button, and right now this is telling us that this is an aluminum 6061.